Hello, I'm Fabian Muehlboeck, I'm from Cornell, and I'm presenting joint work with Ben Greenman and Tate, which is getting F-bounded polymorphism into shape. Now, I want to tell you a story. It is the story of a young researcher. Our hero had some friends in industry who came to him with a problem. They wanted type-safe equality on generic lists. Now, what is the problem here? Classically, the way to implement equality in Java is by overriding the equals method of the object class. The problem with that is that this equals method takes any object as an argument, and therefore we can try to compare the string hello with the number 5, and the type checker will accept this because 5 is a valid object. Now, since the introduction of generics to Java, there is a type-safe way to implement equality. How you would do this is you would define an interface EQ with a type parameter t, specifying which type you want to have equality on. And then you could define your class string to be equatable with other strings. Now, if you want to compare the string hello with the number 5, the type checker will reject this, because 5 is not a valid string. Now we come to type-safe equality on lists. So what our industry friends wanted was to be able to compare lists of strings. So our type checker should accept this. However, the type checker should not accept an attempt to compare lists of functions, because there is no general way of determining whether two functions are equal. So our researchers started thinking about this. Now, what we really care about here are read-only lists and our interface EQ. And what we know about read-only lists is that they are covariant. And we often specify this with a keyword out because conceptually you only get t values out of a read-only list. And furthermore, if you have a list of strings, you can also view it as a list of arbitrary objects. EQ, on the other hand, is contravariant. And the keyword here is in because conceptually EQ only takes t values in. Now, the direction of subtyping here is somewhat reversed because if you have something that is equatable with arbitrary objects, it is also equatable with strings. At this point, our researcher had an idea. What if, he thought, we defined lists of t's to be equatable with lists of things that are equatable with t's? Let's see how this works. Now, what our industry friends wanted was to be able to equate lists of strings. So list of string must be a subtype of EQ of list of string. In order to check this, we need the types on both sides of the judgment to be of the same form. So we apply inheritance to express list of string in terms of its supertype EQ. Now that we have two EQs, we can apply contravariance to recurse on the type arguments. And because of contravariance, we need to swap their sides in the subtyping judgment. Now we have two lists, and because list is covariant, we can apply covariance, again recursing on the type arguments, but this time leaving them on the same sides in the subtyping judgment. Next, we need to check whether a string is subtype of EQ of string, which is true because that's how we define string. So we are done. Therefore, lists of strings are equatable with each other. But notice that this proof relies on the fact that strings are equatable with each other. So this does not hold for lists of arbitrary classes that are not equatable, which is what we wanted. But like all of us, our researchers stood on the shoulders of giants. And some of those giants were not very happy with his solution to the equatable lists problem because it had some properties that had been shown to cause problems with the decidability of subtyping. In particular, some of the giants warned him about expansive inheritance, which in our case means that we smuggled this EQ here in between list and its type argument t, allowing the type to expand in its inheritance clause. And even his own advisor warned him about nested contravariance, which in our case means that because EQ is contravariant, here we nested an EQ inside another EQ. It turns out that they were right to be concerned, and here is why. One could imagine defining a type for trees as a list of its children. Then you could ask whether trees are equatable. Well, I don't know, so let's ask Visual Studio. Here, we have some C# code that encodes exactly the types that we have been talking about so far. We have EQ, we have list, and we have tree. Now we are trying to write a method that takes two trees and equates them using the equal to method. So let's just do that and see what Visual Studio says. And it doesn't say anything, but it just crashes. Now why does it do that? Well, the expected argument type of the equal to method of a tree is list of EQ of tree. This is because tree inherits its equal to method from list of tree. But the argument that we gave it had a type tree, so we need to check whether that is a subtype of list of EQ of tree. So let's do that. First, we apply inheritance to express t in terms of list of tree. Now we have two lists, so we can apply covariance to recurse on the type arguments. Next, we need to check whether tree is a subtype of EQ of tree. Therefore, we need two inheritance steps to go via list to EQ of something. Now we have two EQs, so we can apply contrariance to recurse on the type arguments again on swapped sides, and then we need to check whether tree is a subtype of list of EQ of tree. But that's the type that we had in the beginning. So we ran into an infinite loop, which caused a stack overflow that made Visual Studio crash. Our researcher recognized that this was a problem, but on the other hand, it may have just been a corner case, and our industry friends might not really care about this corner case, especially since we solved the original problem of equatable lists. So he went back to them and presented his solution. But the reaction was not what he had expected. Now, being a good researcher, he of course asked, why didn't they like the solution? And they explained. Well, it really looked like a clever hack, and it looked like it solved their original problem of equatable lists. But what made them cringe was the list of equatables within the inheritance class. This type just didn't make sense to them. Now that was interesting. So on the one hand, we have that lists of strings are okay, but lists of equatables are not okay. Why is that? Well, let's look at how we use equatable. We use it with f-bounded polymorphism. That is, we use it to specify that strings are equatable with other strings, and then we can use it as a type variable constraint to specify that any instantiation of a type variable must be equatable with itself. On the other hand, we do not use them as type arguments, and upon further investigation, our industry friends told us that we also do not use them for method parameters. We also do not use them for return types. We do not use them for fields, and we do not even use them for local variables. So it seems that we have a split here. On the one hand, we have types that are used in recursive inheritance definitions and for recursive type variable constraints. Those are your types like EQ, comparable, clonable, or summable. On the other hand, we have all the other types that are used for type arguments in method parameters, return types, fields, variables. And those are your standard types like string, list, throwable, file streams. And we gave those categories names. We call the first category shapes because they describe the higher level shapes of other types. And we call the second category materials because they are the types that are actually passed around in the program. But let's hold our horses here. After all, we got this split from just talking to our industry friends. And we all know that extrapolating from just a simple example is usually not a very wise idea. So our researcher took an undergrad and let him read all the Java code that he could find and compile to see whether there is an actual pattern here. And the results were quite promising. In total, we surveyed 13.5 million lines of open source generic Java code from 60 projects, including the OpenJDK itself and other popular projects such as Eclipse and Findbugs. Now, across all these projects, we did not find a single class or interface that was ever both used as a shape and a material. That means no type was both used in recursive inheritance definitions and type variable constraints and as a type argument, method parameter, and so on. Great, said our researcher. Set the principle in stone and call it material shape separation. Now, this is a nice observation of how types are used in practice. But it turns out it can also be used for laying the foundation for powerful language features with strong properties. The key insight is the following. Because no type is both used as a shape and a material, and shapes are defined as the things that are used for recursive inheritance, we know that shapes are the only things that are used for recursive inheritance. This means that inheritance for materials is well-founded. So, if you only look at the material components of an inheritance clause, in this case B of C and D of E, you know that the supertypes B and D, and also the type arguments C and E here, have their complete inheritance hierarchies defined independently of A. What that means is that there are no direct inheritance circles, and that makes sense because they are already forbidden by languages like Java and so on. But also you have no indirect circles of inheritance through type arguments. This gives us several nice results, the first of which is decidable subtyping. And in particular, we get decidable subtyping even with naive algorithms, which explains the observation that although subtyping in general has been shown to be undecidable, we never encounter this problem in practice. And we can prove this using a simple measure, which I'm going to show you right now. But first, let's revisit how subtyping works. Imagine there's a material interface for predicates, those are contour-oriented, and there's a material interface for matrices, which are encoded as nested lists. Now we want to know whether a predicate for lists of objects can be used as a predicate for matrices of strings. So let's check that. We have two predicates, those are contour-oriented, so we apply contour-orients to recurse on the type arguments on swapped sides. Now we apply inheritance to express the matrix in terms of nested lists. Then we have two lists, so we can apply covariance. Now we need to check whether list of string is a subtype of object, and that is true for any type, so we're done. But notice that there are two different kinds of rules that we apply here. First, we have co- and contour-orients. Notice that they already make the arguments to the recursive steps at least syntactically smaller, because they only recurse on the type arguments. Inheritance, on the other hand, at least seemingly increases the size of the argument to recursive call. In this case, by blowing up matrix to those nested lists. But intuitively, we know that a matrix of strings can expand more times than those nested lists can. And this expansive power of types is what we're going to use in our measure. So, if you have some type A of t extends B of C of t, and you want to know the number of expansion steps that you can take for some concrete instantiation of A with some type argument tau, you know that you want to take at least one more step than whatever it expands to. What can it expand to? Well, you could apply inheritance, in which case you would get B of C of tau, so we take the size of that. Or you could do a co- or contour-oriented step, in which case you would only recurse on the type argument tau, so you would take the size of that. We don't know which case it will be, so we are pessimistic and take the maximum of the two. Now, if you think a little harder, you can see that similar to how A is a function on types, you can view it as a function on measures. What that means is that given this measure of the type argument, you can return the measure of A with its type argument. Notice that this function definition uses the functions that are similarly defined for the types B and C that appear in A's inheritance clause. And since those might in turn again use the function definition for A, this might lead to unbounded recursion. But for materials, we know that the inheritance relation is well founded, and therefore the size functions for B and C would also not depend on the size functions for A, and therefore the system of equations spanned by our measure functions will always terminate, giving us decidable subtyping on materials. But we also want decidable subtyping in the presence of shapes. So what are these cases? Well, they are the cases when we check whether some type is an instantiation of a shape. Notice that because shapes are not type arguments, there are no other shapes in those judgments. Now what we do in these cases is we apply inheritance, possibly several times, to expand the left-hand side of our judgment to our shape type, in this case EQ, and then we apply either co- or contour-orients, in this case contour-orients, to recurse on the type arguments. But because we already said shapes are not type arguments, we know that the types in the further recursive calls of the subtyping judgment are all materials, and we already established that subtyping of materials is decidable. This means that we have decidable subtyping even in the presence of shapes. And that is a first building on our foundation of material shape separation. But there's space for more, so let me tell you about joins. Joins are defined as the most precise common supertype of two types. You encounter them in things such as conditional expression, where depending on the value of some boolean, you either get a string or a number back. Now what is the type of this conditional expression? It is the join of string and integer. Now what is that join? Well, imagine that both string and integer extend only one type, namely clonable of themselves, which means that their instances can create copies of themselves. Now clonable is a covariant shape because you get instances of the type argument out of a cloning operation. This means that integer and string are both subtypes of clonable of object. But if you look a little harder, you'll see that the result of a cloning operation is also clonable, so they're also both clonables of clonable of object. And if you look even harder, you'll see that they're clonable of clonable of clonable of object, and so on. This is an infinite chain of ever more precise supertypes that has no limit, so the join of integer and string does not exist in this scenario. However, we have already established that programmers don't really expect the types of their expressions to be shapes, so we don't really have to worry about those intermediate shape types. This means that we can concentrate on only materials for the shape types, and in our case of joining string and integer, i.e. the type of the expression where we either get a string or an integer back, the join would be object, and that would make sense because string and integer don't really have that much in common. Now it turns out that if you do that, you always get computable joins. And here's how. Now imagine that you have two types A and B with the common supertype C, and you want to compute the join of two concrete instantiations of them with type arguments tau and tau prime. How you would do that is you would apply inheritance, possibly several times, to lift both of them up to their common supertype representation. Now you know that their join will be a C of something. We won't go into the details of how that something is computed, but there is some recursion on the type arguments tau and e of tau prime. But by the measure that we already gave to show that subtyping was decidable, we know that tau and e of tau prime are smaller than a of tau and b of tau prime. Hence the recursion that is happening on the type arguments will always terminate because of well-founded material inheritance. Therefore, we always get computable joins when we restrict those joins to material types only. So this was the second building we built on our foundation of material shape separation. And now I'll sketch a third. Namely, both of those solutions easily extend to higher kinds. Conceptually, what you have to do is lift up the measure functions to higher order functions. That's all. In fact, because they are built on the same foundation, all of these features can be combined nicely. So our researcher went back to his friends in industry and showed them our results and the foundation that we had built them on. He even told them that we now think that we have the blueprints for solving the problem of conditional inheritance, which in turn would solve their original problem of having lists be equatable if and only if the type arguments are equatable. Now they were a bit skeptic at first, because they were the team at Red Hat working on the new programming language Ceylon, which makes very heavy use of generics. But they implemented a test version of their compiler and ran it on all the Ceylon code that they knew of, and determined that their codebase was still compatible with material shape separation. They therefore plan to include it in the next major release of Ceylon. In summary, I showed you 3 results which we got by exploiting a pattern that we found when observing how people in industry actually use type system features. And we called this pattern material shape separation. So by observing how type system features are actually used in practice, we can get powerful language features with strong properties. And finally, bring F-bounded polymorphism into shape.